Okay, we ever take another integral from the MIT Integration Bee 2006. This was problem 31. We had the integral from 0 to pi over 2, natural log sine x dx. Okay, I always like problems like this just because with the natural log with the trig function inside of it, it's kind of hard to deal with. But what we can do, I think, is use the bounds. What I want to do for this is just use King's principle. Okay, so using our formula that we have over here to the right, what we want to do is we just want to add up our bounds, our a and b value. So when we do that, when we just add pi over 2 to 0, we just get pi over 2. So this a plus b value is going to be pi over 2. We want to compute for this f of pi over 2 minus x. And this is going to give us a quick way to just transform this integral without having to do out the steps of the u substitution. So when we do this, our bounds stay the same. So this is going to be going from 0 to pi over 2. Then we're going to have natural log. Then inputting into the sign, we're going to have this pi over 2 minus x. We're going to end up with sine pi over 2 minus x here dx. But now here on sine pi over 2 minus x, we have the complementary angle formula that tells us that this thing is going to be the same thing as cosine of x. So we can do a quick rewrite over here, and what we get is, this is kind of interesting, we just have natural log. Now, instead of having sine x, now we have cosine x dx. And I think it might be fair to think that we've accomplished nothing, because this integral we have right here, this is just as hard as what we started with. There's really no difference, right? Well, where we can gain an advantage is just by labeling our integral. Our original integral we'll call I. We transformed it all the way down here, and this is just I, so we can actually add these two together and see what happens. Now we'll have two copies of our integral 2I, and so now what we have is we've got natural log sine x plus natural log cosine x here. But then log properties is going to allow us to combine these, right, and multiply it together. So when I rewrite again, now what's going to happen is we have natural log of sine x times cosine x dx. But the nice thing about this here is it's really close to our double angle formula for sine. I just need to multiply it 2. Then by doing that, what we have here, this whole thing is just sine 2x when we rewrite it. But I don't want to change it, right? So let's just divide off that 2 right here. And then I can actually use log properties on this again, but let's just bring down our 2i here. And actually, let's just get rid of this 2 so we can isolate our I. So we can divide by 2 on both sides. I'll multiply by 1/2 over here. And now over here, we'll split this up with log properties. I can now, because we're dividing here, I can write this as subtraction and split this into two integrals. So for like the first integral, we're just going to be going 0 pi over 2. This first one's just going to be natural log sine of 2x. And then let's split off this 2 with the log properties into a completely separate integral. So we'll have our dx here. This is going to be minus natural log of 2 here. But I need to distribute in this 1/2. And now at this point, ln2 is just a constant, so this one's going to be easy. But coming back to this, what have we done? We're really back to what we had. This isn't any easier than what we started with. So in a way, we still haven't gotten anywhere. Okay, so we still have some more work to do on this first integral. What I want to do is I want to try to clean up this angle because we were dealing with sine x here. Let's get this back. So what I can do is, so let's just do a substitution on 2x to try to simplify this. So I'm going to do very simple u substitution, u equal to 2x. Then du is going to be just 2 dx. And then let's just go ahead with this over here. So first we'll update our bounds, plugging pi over 2 in here. Upper bound becomes pi. Plugging 0 in here, lower bound 0. Then transforming this, it's just going to become natural log sine of u. And for our dx value, actually let's just go ahead and solve for dx real quick. I can write this as du over 2. So doing this, we'll have du. But for this 2, let's bring it out front as a 1/2 here. And then let's just deal with this thing while we're at it. So I can bring the ln2 out front because it's a constant value. So I can write this as minus natural log 2 over 2. Integrating, we get x, and this just needs to be evaluated from 0 to pi over 2. Now, of course, 1/2 times 1/2, I can just fix that. I'll write that as 1 over 4. And let's just do a variable change here because we've got everything else in terms of x. So let's get this back in terms of x. This is a definite integral. I can change the variable name, so put it back that way. And then what I notice here is we almost have our original integral right here. We got everything the same. We got our ln sine of x, but we've got a different upper bound. So all I really need to do to be able to kind of add this back to our original integral is divide this upper bound. And we actually have a principle that's going to help us with this. Okay, now I have the principle I want to use over here to the right. We're just notice if our upper bound here is 2a, it does exactly what we want. It just divides this in half and just gives us our a. So that's what we want to happen here. And the only thing we need to do is we need to bring a 2 out front. But this only works with this condition here. So we actually have a test. Our f of x on this is going to be this. And so what we need to do for this test is check our f of 2a minus x value. In this case, that's just going to be f of pi minus x. So if we do that, we're going to have natural log sine pi minus x. But what's going to happen, this here, this is actually the supplementary angle formula. This is the same thing as sine of x. And so what's going to happen, this becomes ln sine of x, and that's exactly this value, our f of x. So this condition here is true, and therefore we can use this principle down here. So going ahead with this, we have our 1/4, but let's bring out this, now we have to bring out this 2 in order to do this. We'll have, now this is going to become 2/4. We can cut our upper bound in half, so now this is going from 0 to pi over 2. This just transform again, just the same thing, ln sine of x dx. And actually, let's just deal with this right now. Now for the 0 value, that's not going to matter because that's going to be 0. And so we just need to plug in pi over 2 here, and this is going to become minus pi natural log 2 over 2. Now this here is going to become just 1/2, right? Okay, now I think we have this perfectly set up because what we have right here, this thing is exactly our original integral, so we can label this I. Then identifying this as I, we can just kind of come over here and create a little equation that I is going to be the same thing as 1/2 I minus this piece, but then I can just subtract a 1/2 I on both sides here, like this. That's going to cancel off here, and then what we have here on the left side is just going to be 1/2 I equal to this, which is minus pi ln 2/4. To get rid of the half, let's just multiply by a 2 on both sides, multiply by 2 here. And so now on the left side, we've just isolated our goal of I, and so multiplying in the 2 here, for my final solution of this, we just get minus pi over 2 ln 2. Okay, there you have it. Really good problem from MIT 2006. Thanks everyone for watching. Have a good day.